Hi everyone, welcome to Group T10's material selection project on railroad tracks. The product we decided to select was a section of a railroad track in front of E5. Now to a little background information on the product. The railroad tracks are generally used for the ION LRT transit system in the Waterloo region. On rare occasions, freight trains do use this railroad. The rails were installed approximately 6 years ago when construction began. We expect these rails to be made from 1080 carbon steel, as it is the industry standard when it comes to the manufacturing of railroad tracks today. The railroad tracks are exposed to Canada's harsh environment year-round, which means temperatures from around -30 to +40 degrees Celsius, along with snow, rain, ice, etc. Next, let's talk about the visible corrosion present. The section of the track that we observed appeared to have some surface rust. This can possibly be caused by galvanic corrosion from the exposure of salt, rain, etc. We also observed some pitting corrosion, which is due to surface scratches and the roughness of the track itself. Finally, in consideration, the railroad track holds up well against any major corrosion considering Canada's harsh environment and weather patterns. The first part of the manufacturing process for railroad tracks is casting. Most of the time, railroad tracks are made from recycled steel, food cans, and leftover rails from the manufacturing process. The process begins when the scrap material is melted down in an electric arc furnace at around 1650 degrees Celsius. The steel is then poured into a brick ladle where carbon and manganese are added along with some other elements to strengthen the steel. The molten steel is then cast into blocks called blooms for further manufacture. The next part of the manufacturing process is hot rolling. The blooms are first heated at 1250 degrees Celsius for 5 to 7 hours. They are then sent through a rolling mill where the blooms are rolled out to about 4 times their original length. They are then reinserted into a furnace where they are briefly reheated to prepare for more hot rolling. The elongated blooms are then passed through 3 consecutive rolling mills several times, where the railroad track takes its final shape. The final part in the manufacturing process is air cooling and quality control. The railroad tracks are first left out to cool for about 10 hours after hot rolling, or until they reach around 90 degrees Celsius. The railroad tracks are then sent through a series of vertical and horizontal rollers that slightly bend the tracks to straighten them out. They are then cut into the industry standard length of around 25 meters and visually inspected for any defects seen.
When deriving the materials performance index equations, we made several assumptions. Through the research we found that each ion train weighed about 50,000 kilograms and had 12 wheels. Assuming that the weight was evenly distributed to each wheel would support about 4,166.7 kilograms. We also simplified the rail's geometry to a rectangular beam to simplify the requirement equations. We used the dimensions for the rail's weakest part, which should result in us choosing a material which exceeds the actual needs of the rail. Our overall goal was to reduce the mass of the rail, which would lead to lower production, transporting, and installation costs. The mass was calculated by multiplying the volume of the beam by the density of the material. These are the functional requirements which needed to be met by the beam of the selected material. First, the beam should have a load capacity of more than 4,200 kilograms. It should have a maximum deflection of less than 1 centimeter when loaded, and it should be able to take the load at the center of a 30 centimeter unsupported beam with a height of 14 centimeters. It should also have a hardness greater than 350 on the Vickers scale. For constraints, the material must be weldable, malleable, recyclable, and cost less than $1 Canadian per kilogram, and the 0.3 meter beam must weigh less than 30 kilograms. Two MPI ratios that were derived using those requirements were yield strength over density and Young's modulus over density, both of which we wanted to maximize. We then found the slope and points on each of the MPI cutoff lines. A more in-depth derivation of the MPI ratios can be found in the supporting document. Here is the CES plot with the Young's modulus over density MPI cutoff line. Here is the CES plot with the yield strength over density MPI cutoff line added. To make sure that all the functional requirements and constraints were met, we added some additional limits. First, the price had to be lower than $1 Canadian per kilogram, and the hardness had to be above 350 on the Vickers scale. It also had to be weldable and recyclable. 28 materials met all of the functional requirements and constraints. Cast iron did have the cheapest raw material cost, but was deemed overall more expensive than carbon steel due to the machining process which would be required. This made the 1095 carbon steels the least expensive. 1095 carbon steel, which was water quenched and tempered at 205 degrees Celsius, was selected since it had the highest hardness, which would extend the rail's lifetime by reducing wear. This material also used water for quenching and was tempered at the lowest temperature, further reducing manufacturing costs compared to other options.
At the end of the material selection process, 1095 carbon steel quenched in water at 205 degrees Celsius was selected. This material is very similar to the 1080 hot rolled steel that was determined to be the original material of the rail. After some research, it was determined the main reason for the original rail manufacturer to choose an inferior 1080 steel lied in its ease of manufacture. During the cooling or tempering process, the 1080 steel has a carbon content that is very close to the eutectic point, meaning a very pure perlite structure is formed after equilibrium cooling. This perlite structure strikes a balance between soft, ferrite-containing hypoeutectoid steel and harder, cementite-containing hypereutectoid steel. Although 1095 steel can be quenched and tempered to be tougher, harder, and stronger than 1080 steel, the extra quenching and annealing required to do this outweigh the benefits in the manufacturer's eyes. However, we believe our material is superior despite the increased steps required to manufacture it. As further proof, some railroad companies in Europe currently have decided to improve their tracks via our recommended quenching and annealing techniques in a process called head hardening. During the process, the top of the rail that contacts the wheel of the train car is heated, quenched, and tempered to exhibit improved toughness and wear resistance. The bottom of the rail, that is not as affected by the quenching due to hardness penetration, is left softer than the top to help absorb vibrations and noise created by the wheels to provide a smoother ride. In conclusion, using a 1095 steel head quenched at 205 degrees Celsius would benefit all railroad users. For passengers of trains, it would result in an improved ride with less harsh vibrations. For companies and railroad owners, the improved durability of the railroad would mean less frequent repairs, and reconditioning of the tracks would need to be required. For these reasons, we believe our selected steel is superior to the original. Please see our attached document for more information on this.